Alright gang, here we go. So this is Chem 1, Unit 2, Chapter 21, Nuclear Chemistry. So the first half of Unit 2 talked about Chapter 3. We talked about atomic structure, atomic history, mole calculations, and now we're jumping to Chapter 21, which is obviously the next obvious jump after Chapter 3. So we're going to be talking about nuclear chemistry. So when you see nuclear chemistry, the first thing that should pop into your head, you see the word nuclear, and you should automatically start thinking about the nucleus, right? And that's really the difference between nuclear chemistry and the rest of chemistry. All right, so here, go ahead and pause the video, fill out your note packet, or read through these bullet points, okay? We're just going to talk about these real quick. So this is the difference between chemical and nuclear reactions. And notice how in a chemical reaction, it's all about the electrons. So we're trying to see, in a chemical reaction, in a sense, we're losing or gaining or sharing or giving away or, electrons. Okay, that's essentially what's happening in a chemical reaction, and these happen because our elements are trying to become like their nearest noble gas. The long and the short of it. Okay, so they're trying to reach stability. In nuclear reactions, you have unstable isotopes. Okay, we call these radioisotopes, but an unstable isotope, remember, an isotope are elements of the same or nucleuses of the same element that have different number of neutrons. Okay, and they try to reach stability by undergoing changes in their nucleus. All right, so that means that they're going to be losing or gaining protons or neutrons. Okay, or trading them out, and there's lots of different ways, and we'll go through all that stuff. All right, as we move through this unit. Okay, so notice how the similarity between these two is that they're both trying to go towards stability. Okay, that's the big to do in both reactions. In a chemical reaction, they try to reach stability by getting the same number of valence electrons as their nearest noble gas. In nuclear reactions, they're trying to gain stability by getting a perfect ratio of protons to neutrons. All right. In chemical reactions, we can affect the speed or even how much of the reaction occurs by changing the temperature, the pressure, or adding or taking away catalysts. All right, so like for example, you've probably taken the glow stick, right? You take a glow stick and you crack it, okay? And so you had it out there, you were trick or treating, you had a glow stick, and then you're like, oh, I want this glow sticks to still be good in the morning. So where do you put it? Well, you put it in the freezer, right? So you stick that thing in the freezer, you come back the next day, and it still works for a little bit longer. Now the reason that works is because it slowed down the chemical reaction. Okay, so there was a chemical reaction that occurred when you cracked that glow stick. It started mixing two chemicals together, and you could slow it down by putting it in the freezer. Okay, that does not work, okay, in a nuclear reaction. As soon as that thing starts to decay or react, you can't slow it down. Okay, and so it's already starting all on its own. Okay, in a chemical reaction, no new elements are formed. So let's say we take hydrogen, H2, and we react that guy with oxygen. Okay, we mix those two together and we get water. Okay, so this reaction here is actually explosive. Okay, we could balance this thing out. Okay, so hydrogen gas, you've probably heard of the Hindenburg. Okay, the Hindenburg blew up because they had hydrogen in this big thing, and there was a spark, and then it mixed with the oxygen that's in the atmosphere, and then the Hindenburg blew down or burned up and fell down. Okay, so same idea here. Notice that in our equation here, we have 4 hydrogens, right? 2 diatomic hydrogens, and we've got 1 and 2 oxygens, and then we've got here 4 hydrogens and 2 oxygens. Okay, so notice that we don't have any new elements. Over here we've got hydrogens, we've got oxygens that we start with, and then we just combine them in a new way. Okay, in nuclear reactions, we do get new elements. Now, when I say new elements, I don't mean like new elements, like never before discovered, although that could happen. Okay. However, what we really mean is that they're new elements. So, say if you have a box that has uranium in it and it undergoes decay. Okay, you're going to have new elements within that box that weren't there before. If there was just uranium in there and it undergoes decay, you're going to have new elements. All right. Now, comparatively, nuclear reactions release a lot more energy, orders of magnitude more. Okay, chemical reactions do release energy quite a bit. Like the Hindenburg, you felt the heat from the Hindenburg because it was releasing energy. The energy is heat. Okay. Now, nuclear reactions, though, will produce much more energy when you compare the magnitude or the amounts that you start with. Okay, nuclear reactions are also spontaneous. In chemistry, when we say spontaneous, really we mean that it happens all on its own. Okay, now think again about your hydrogen explosion, right? For the Hindenburg to blow up, in order for that to occur, there had to have been some sort of spark. The Hindenburg flew lots of flights. I'm not sure the exact number, but it flew several flights at least, back and forth, wherever it was going, taking passengers from point A to point B without blowing up. Suddenly there's a spark, and boom, you get a problem. Okay, but without that catalyst, or without that start point for your explosion, the reaction wasn't going to go. Now, some chemical reactions are spontaneous, but in a nuclear reaction, all nuclear reactions are spontaneous, meaning they're occurring on their own without any input for us. And we cannot change the temperature, or we cannot change the speed or our reaction itself by changing the temperature, pressure, adding catalysts. Okay? Nuclear reactions just simply can't be turned off. Okay? All right, so let's do some definitions here. All right, go ahead and pause it, fill out your notes, and we'll blow through this right quick. All right, radioisotopes are defined, they are the unstable isotopes because they have unstable nuclei. Okay, now make this note, okay? Stability, the stability of your nucleus, right, is defined by the proton to neutron ratio. Okay, the stability of your nucleus is defined by your proton to neutron ratio, and we'll go over exactly what that ratio needs to be here in a second. But essentially, your nucleus, the stability of it, or how stable it is simply you're going to look at the number of protons and look at how many neutrons you got. If you have the right number of both, you've got a fairly stable element. If you don't have the right number of both, then your thing is not stable and you undergo radioactive decay. Okay, radioactive decay occurs when your unstable isotope, or your radioisotope, gives off radiation. Radiation is defined as the penetrating rays and particles emitted from a source, and the source is simply the radioisotope. Okay. So when something undergoes radioactive decay, the whole idea is that it's got an unstable amount of neutrons or protons, or both. Okay, that ratio is off. So the decay changes the number of protons or changes the number of neutrons, or sometimes both. And we'll, in the next video, we'll kind of talk about what all that looks like. All right, so here's just an example of radioactive decay. Up here at the top, we've got uranium-238. Okay, so this is a fairly stable isotope, but not completely stable. All right, so and it'll undergo all of these decays. So first it'll undergo an alpha decay, then a beta, then a beta, then an alpha, then an alpha, then an alpha, and you can see what it turned into. And we can go all the way down. All of these guys are unstable until finally it gets to lead-206, and this is a stable isotope. Okay, so it goes through all of these different stations, you know, and notice there's even a lead up earlier, right? There's a lead-214, but lead-214 is also not stable. Okay, so it kind of keeps going, so on and so forth. All right, now this is a very important slide. Okay, this is called the band of stability. Now remember, we said stability. Remember, stability is defined by the proton to neutron ratio. Okay, so we really care about how many neutrons we have to how many protons we have. All right, so on this graph here, we've got the number of neutrons are in the y-axis, okay, and the number of protons are in the x-axis. Okay, so as this black line here, now don't let this confuse you, this black line here represents the 1-to-1 proton to neutron ratio. So this is assuming that it's perfect. When you've got 10 protons down here, you've got 10 neutrons right here. All right, and you're just right at that point, and then 20, and then 30, 40, 50, 60. So you're 1-to-1 ratio. All right, notice that when you're down here in the low atomic numbers, like less than 15 or so, the ratio is pretty much established at 1-to-1. Okay, that you're pretty close to this, the perfect ratio being 1-to-1. As you start to get to a higher number of protons, you need more and more neutrons to make it stable. Okay, so note when you get to like about 50 or so, you need about 1.5. Okay, so 50, 55 or so, you need about a 1.5 or 1 proton to every 1.5 neutrons, or 1.5 neutrons to every 1 proton. Okay, when you're up in the high levels. All right, so and we'll talk about that here in a minute. I've got a slide with some bullet points to help you with your notes. Okay. All right, here on the right, so the blue dots here, these are the stable isotopes. The green ones are stability-like. They're slightly stable, so we actually find those isotopes in nature, but they're decaying trying to get to the blue areas. Okay, so this is kind of a zoomed-in section of our stability band here. Okay, and so we've got these blue lines, that's the stable ones. Okay, and then if our isotope happens to, so say our isotope is this guy right here. We've got this isotope right here. It's going to, what this graph tells us is it's going to have what's called positron emission or electron capture, and that's going to force it to kind of go over this way, right? And then we'll be over here, and then we might undergo beta emission, which might shove it down this way. So really, if if this is our band of stability, really we're just going to be jigger jogging across this line until we reach an isotope that happens to be right on the band of stability. Okay, so that's the entire idea of this decay, that it just kind of jigger jogs it around until you get to a stable isotope. All right. Stability of the isotope is based on proton to neutron ratio. Okay, if you have less than 20 protons, now this is something you should get used to. When you see the capital letter Z, that implies you're talking about protons. Okay, so when you have 20 protons or less, the most stable proton to neutron ratio is 1 to 1. Okay. So add this line to your notes, okay? When you're above about 55, okay, so we'll say above, 55 or above, right? Your stable ratio is a proton to neutron ratio of about 1 to 1.5, okay? So write that in your notes, okay? So when you're about atomic number about 55 and above, all right, your perfect proton to neutron ratio is about 1 to 1.5. Right? So notice as you get bigger and bigger, you need more and more neutrons to stabilize it. Now, one thing you should note is that past number 83, there's no stable isotopes. There's no stable isotopes for that particular element. So bismuth is atomic number 83, and polonium is right next to it. Bismuth has a stable isotope. It has an isotope that will not give off radioactive decay. You go one over to polonium, and suddenly you're in trouble. You cannot, or after that point, you will undergo radioactive decay at all isotopes. Okay. Now, all elements have radioactive isotopes, but the trick is that past 83 they don't have any stable isotopes. Okay. All right. So I'm sure you're sitting there like, wow, nuclear chemistry, this is pretty great, but I wish we could do some math, right? So you're in luck. Here we go. We're going to do some math here. Okay, so Half-Life, not only is it a great video game series that they need to come out with the third one for, okay, but this is what it's defined as scientifically. Half-Life is defined as the time needed, okay, for 1/2 of a sample to decay. Okay, so if you start with a sample of like 50 grams of whatever it is, so 50 grams of uranium, one half-life goes by and I have 25 grams. Okay, pretty simple. All right. After each half-life, half of the existing radioactive atoms have decayed into new elements. So the neat thing about this is that every radioisotope, remember that means unstable isotope, every radioisotope has a unique rate of decay that's measured by its half-life. Okay, so we can use these unique rates in order to identify many different things. So you've probably heard of like carbon-14 dating. That's how we know how old different artifacts are, dinosaur bones, so on and so forth. We can use radioactive dating of carbon-14 because it's always a unique rate in order, and you can't change it. As far as we know, we can't make it go faster or slower. Okay, and so we can use that to determine how old it is, for example. Okay. So here's a list of different half-lives. Now I think this is super fascinating, okay, because the stabilities are really quite drastic. So just look at these two real quick, all right? So if you look at uranium-237 versus uranium-238, what's the difference between the nucleuses of this guy versus this guy? Well, the only difference, you know they have to have the same number of protons because that's how we know it's uranium. Okay, uranium is atomic number 92. You know they both have to have 92 protons. So what's the difference? Well, the only difference is the fact that uranium-237 has one less neutron than uranium-238. And look how much it affects its half-life. Okay, uranium-238 that we looked at earlier, its half-life is 4.46 times 10 to the 9th years. So that's like 4.5 trillion years. All right, that's its half-life. Okay, 4.46 times 10 to the ninth years for half of it to decay. Now, if you take one neutron off of that nucleus, its half-life goes from longer than the history of the Earth, okay, from the solar system creation, to a mere 6.75 days, not even a full week. All right, that's how, like, just that one neutron affects the stability of the isotope that much. Pretty wild. All right, here we go. Now we're going to get into the math here. All right, so carbon-14, it says, emits beta radiation and decays with a half-life of 5,730 years. Okay, so just to recap here, this symbol right here, this means half-life. Remember, lowercase t means time, and this little 1/2 as a subscript implies that you're talking about half-life. All right, so its half-life of carbon-14 is about 5,730 years. Assume you start with a mass of 2.0 times 10 to the negative 12th grams of carbon-14. All right, so first we have to say how long is 3 half-lives. Okay, well, each half-life is 5,730 years, so really we just have to take 3 times 5,730, and we can get the number of years. So we'll just take 3 times 5,730, and we get 17,190 years. 17,190 years. So if 3 half-life goes by, it took 17,190 years for it to occur. And it says how many grams of the isotope remain at the end of 3 half-lives. Now, half-life math can get quite complicated using natural logs and powers and all sorts of crazy things like that. But for our purposes, we're going to keep it nice and simple. All right, so this is how I want you to do all half-life equations, okay? So you're going to write down how much you started with, all right? So you say 2.00 times 10 to the minus 12th grams, okay? And 3 half-lives go by, so you're going to draw an arrow, and you're like, okay, that was 1 half-life. So you draw an arrow, do a circled 1. All right, 1 circle. Now divide that guy by 2, so it becomes 1.00 times 10 to the minus 12th. Right? Because if a half-life goes by, that means we have half of as much as what we started with. So we have 1.00 times 10 to the minus 12th. All right? Then the second half-life goes by, we divide it by 2 again, and we say, okay, we got 0.50 times 10 to the minus 12th, okay, grams. All right, but it said 3 half-lives go by, right? How many remain at the end of 3 half-lives? All right, so we got to do it one more time. We'll draw an arrow. We'll do 3 with a circle, and we get 0.25 times 10 to the minus 12th grams, all right? Now, we could be, so this is our answer, but we could be cool. We could say we have 2.50 times 10 to the minus 12th, now, or times 10 to the minus 13th. This number is better for a couple of reasons. Number one, it's in scientific notation, which is always better. Okay, this is scientific notation, and also we have the correct number of sig figs, which we'll talk about at a future date. So don't worry about it now, just if you come back looking at this later, maybe for our final review or something like that. Okay, all right, one more problem that will be done. Manganese 56 is a beta emitter with a half-life of 2.6 hours. All right, what is the mass of manganese 56 in a 1 milligram sample of the isotope at the end of 10.4 hours? So this is essentially the same problem as before. However, we don't know how many half-lives went by, so we have to calculate how many half-lives went by first. All right, so 10.4 hours went by, right? And we know that a half-life takes 2.6 hours. Okay, so if we divide 10.4 by 2.6, we can figure out how many half-lives went by. So 10.4 divided by 2.6, we get 4 half-lives. So there were 4 half-lives that went by in our time here. Okay, so our sample is 1.0 milligrams. All right, so the first half-life goes by, arrow with the circled 1, we get 0.5 milligrams. All right, second one goes by, 2, circle, 0.25 milligrams. So on and so forth, right? All right, 3, we got to do this 4 times, right? Third half-life, we get 0.125 milligrams. All right, and then number 4, divide by 2 one more time, and we get 0.06. Oh my goodness, my brain's freezing. 0.125 divided by 2. Yeah, 0.0625. All right, 0.0625 milligrams. All right. And then once again, if you're coming back later and you want to know the sig figs, this has 1 sig fig here, so we need 2, or this has 2 sig figs. This has 2 sig figs here, so our answer needs 2. So 0.063 milligrams. And Bob's your uncle. So there you go. So at the end of 10.4 hours, our original 1 milligram sample of manganese 56 has 0.063 milligrams remaining. All right, so do some practice problems, get ready for your quiz that's coming up. Let me know if you have any questions, and I'll see you on the flip side.